All right, chemistry, this is your video lecture for chapter 6, section 4. We're going to talk about the last type of bonding that we're going to hit in this chapter, metallic bonding. And so we've seen combinations of the two major types, the two major divisions of elements, metals and nonmetals. We've seen that if two nonmetals bond together, it's going to be something that we call a covalent bond. It's a sharing of electrons. We've also seen that if we have a nonmetal bond with a metal, we're going to call that ionic bonding because there's going to be a transfer of electrons from the metal to the nonmetal. Well, the only other combination we have is metals bonding with metals. And we have the very creative name, metallic bonding, to describe that. Now, in metallic bonding, we're not going to have a sharing of electrons, and we're not going to have a transfer of electrons. We're going to have something that's kind of a mixture of both, and it's going to have a special name. We call it the electron C. So, at the end of this video, I want you to be able to describe the electron C model of metallic bonding and explain why metals are good electrical conductors. Also, explain why metal surfaces are shiny. Then explain why metals are malleable and ductile, but ionic crystalline compounds are not. So, chemical bonding is different in metals than it is in ionic, molecular, or covalent network compounds, which is a different type of bonding that we're not going to work with a whole bunch. The unique characteristics of metallic bonding gives metals their characteristic properties, like what you think of when you think of a metal, like electrical conductivity, thermal conductivity, malleability, ductility, or a shiny appearance, also known as luster. So malleability is the ability of a substance to be hammered or beaten into thin sheets, whereas ductility is the ability of a substance to be drawn, pulled, or extruded through small opening to produce some sort of wire. And so if we look graphically at representations of these different types of bonds, we already know that for covalent bonding, we have this overlapping of electron clouds, and we have a sharing of electrons right here in the middle. This would be a nonpolar covalent bond because it's just chlorine bonded to itself. So it's going to be an even sharing, an electronegativity difference of 0. We have ionic bonding, which we went over last section, where we have a complete transfer of an electron. Here it's a potassium chloride, so this is a potassium atom. It ionized, transferred its one electron to a chlorine atom, making it a chloride ion. And we have the electrostatic attraction between a positive charge and a negative charge. But with metallic bonding, we have a whole bunch of metals, and remember, metals want to donate an electron, but there's nothing to take in that electron. Just like here, the chlorine is a halogen. It's more than happy to take in that one electron. But if we have a sample of only metal atoms, they're all metal atoms. They all want to donate. None of them want to take. And so there's going to be this weird balance of transferring and sharing and not actually owning electrons that's going to bind all of these metals together. So to get a better idea of what I mean by this weird combination of kind of sharing, kind of not, kind of transferring, kind of not, never really owning an electron, in a metal, the vacant orbitals in the atom's outer energy levels overlap. Okay, not unlike a covalent bond, overlapping orbitals. This overlapping orbitals allows the outer electrons of the atoms to roam freely throughout the entire metal. They move around wherever they want to, as long as it's in the sample of the metal, the outer electrons just move around. These atoms, because they can move around, they're not in one location, they're not localized, they are considered to be delocalized, which means they do not belong to any one atom, but move freely about the metal's network of empty atomic orbitals that are overlapping. These mobile electrons form what's known as a sea of electrons around the metal atoms, which are packed together in a crystal lattice. Here's a crystal lattice yet again. The chemical bonding that results from the attraction between metal atoms and the surrounding sea of electrons is called metallic bonding.
Metal atoms have few electrons in their valence shell, and these are relatively weakly held. Though metal atoms group together in a crystalline lattice structure, they have very different properties to the ionic solids. For example, solid metals are able to conduct electricity. This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom. Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations. The structure is held together by the strong electrostatic force between the sea of valence electrons and the metal cations. This is called metallic bonding. The electrons are constantly on the move, so the bonding acts in all directions. Metallic bonding is powerful enough to overcome the force of repulsion between the closely packed cations. The high melting points of most metals indicates the strength of the metallic bond.
And so that's the nature of the electron. See, that delocalized electron is actually being attracted to multiple cations at once. And one cation is being attracted to multiple electrons at once. It's a multi-directional attraction, just like we saw in the ionic crystal lattice. The big difference here is that there's no negative ion. That negative charge is just to an electron. So let's use that idea of the sea of electrons to describe the two properties of metals we've already defined, malleability and ductility. As a quick reminder, malleability is the ability to hammer or flatten metal into a sheet, whereas ductility is the ability to draw that metal into a wire.
The malleability and ductility of metals are possible because metallic bonding is the same in all directions throughout the solid. When a piece of metal is hammered, one plane of atoms in a metal can slide past another without encountering any resistance or breaking any bonds. When a piece of metal is drawn or squeezed, the atoms slide past each other without breaking bonds. This ability of metals to be shaped by hammering or drawing is the basis for much of the technology that we use in our daily lives.
So if I pause Robot Lady and I go back to this image right
of metals to be shaped.
Oh, didn't go back far enough. Right there. We saw that as we were drawing this metal into a wire, right here, we saw that as these positive ions and these negative electrons were moved around, they never lost attraction, that electrostatic attraction to the things surrounding them. And so that means even though they were moved, they moved together and they maintained attraction. They maintained attraction. And so they did not shatter. They did not break, as opposed to the ionic crystal, that if you apply enough force, you can actually get those ions to shift over one. But in that case, now the negative ions line up with negative ions, and the positive ions line up with positive ions, and they create a huge repulsion force, causing the crystal to shatter. That doesn't happen with metals because those electrons are free to move. So no matter how you force the cations to move, the electrons will move to maintain attraction and maintain the stability of the structure. All right, guys, this is a pretty darn short section, so I will see you next period.